All right, so let's look at two examples where we're going to try to identify the appropriate test to apply for a given series and then actually determine if the series converges. And if you recall, we created a list of 6 different tests that we've discussed thus far, and I suggested just working down the line. All right, so here's the 2 series we're going to look at, and both are going to be from n equals 1 to infinity. And the first one is 2 over n times n plus 1. And so the first thing we'll do is we'll do nth term test. The limit as n goes to infinity of an. In this case, notice the denominator grows, the numerator stays the same, and so we'll get 0. And so this would be inconclusive. And for the second one, I'll just go ahead and do both of them in parallel here. The nth term test, let's see, limit as n goes to infinity of an. That one's a little harder. So let me simplify that first of all. Notice we have a factor of n in both the top and the bottom. So we could cancel out one of those. We'll be left with n over root n plus 1. And now the numerator has n to the first power. The denominator, well, the 1 is not growing. And if you just ignored that, it would look like n to the 1/2 power. So that hints that the numerator might be growing faster. But to check that, what we might do is divide by square root of n. And that would give us, on top, we would get n over root n. That is just root n. And on bottom, we'd have root n plus 1 over n, which we can simplify to root 1 plus 1 over n. And notice, as n goes to infinity, that looks like the numerator is going to approach infinity, and the denominator is going to approach root 1 plus 0, which is infinity. And so the terms in this series are actually growing. They're going off to infinity. And if the things that we're adding up are going off to infinity, the nth term test tells us that this must diverge. Okay? So this one, the sum of an diverges. We can stop there. The nth term test is sufficient. Unfortunately, that doesn't always work, as we see from the example on the left, and so we'll have to work a little bit harder on this one. At the next point, you'd say, well, does that look like it is geometric? And for geometric series, remember, we're looking for things like some number raised to the nth power. Clearly, that does not apply to the series on the left here. Is it telescoping? This one's a little bit harder, but it turns out that we could actually try to rewrite this in a more convenient form if we were to use partial fractions here. So let's try partial fractions. Let's try to decompose 2 over n times n plus 1 into 2 fractions, some number over n plus some number over n plus 1. And we can multiply through by the denominator, and we'll get 2 times an plus 1 plus bn. If we choose to plug in n equals 0 here, we'll get 2 equals a. And if we choose to plug in n equals -1 here, we'll get 2 equals -b. And so there we go. We've got, this is just 2 over n minus 2 over n plus 1. And when you rewrite the terms in the series that way, it seems more plausible that we could have this telescoping phenomenon in place here. All right, so let's sort of reassess our problem. We now have 2, and I'll even factor out the 2, times 1 over n minus 1 over n plus 1. And so we could write down some partial sums here and some individual terms. Start with the terms. A1 would be 2 times 1 minus 1/2. A2 would be 2 times 1/2 minus 1/3, and so on. And our partial sums would therefore be S1 is just A1, and S2 would be 2 times, and then I'm just going to factor out a 2, so we'll have 1 minus 1/2 plus 1/2 minus 1/3. And we see there's some nice cancellation there. 1 minus 1/3 is what's in parentheses. And if we were to go a step further, A3 would be 1/3 minus 1/4, all times 2. And S3 would therefore be equal to 2 times 1 minus 1/3 plus the last term. And at that point, we're left with just 2 times 1 minus 1/4. And I think it's clear what the pattern is now. The nth partial sum is going to be 2 times 1 minus, and then the number in the denominator here always seems to be 1 more than the subscript. So we had 2 and 1, 3 and 2, 4 and 3. And so if we have n for our subscript, we should have an n plus 1 over here. And if those are the partial sums and we want to know what the sum of all of them approaches, we can look at the limit as n goes to infinity of that quantity, which would be the limit as n goes to infinity of, let's see, that's 2 times 1 minus 1 over n plus 1. Well, that second term definitely wants to go to 0, and so we're going to be left with just 2. So the nice thing about a telescoping series is not only can we tell that this converges, but we can tell exactly what it converges to. And so if you can do that, by all means, take advantage of the fact that it's telescoping. Now, let's suppose for a second that we did not recognize that this was a telescoping series. Could we still have been able to tell that it converged? All right, so we'll go back to the original series. We had an was 2 over n times n plus 1. And we want to be able to apply a test, and we convinced ourselves that geometric series were out, the nth term test was inconclusive, and maybe we didn't recognize that it was telescoping. What is our next option? Well, after that, we have the integral test, we have the direct comparison test, and the limit comparison test. And actually, any of those tests could be successfully applied here. Let's go with the integral test. We already showed that this can be written as 2 over n minus 2 over n plus 1. And you can show that this is a decreasing and positive function because the denominator is getting larger and larger and larger. And so what that means is we could look at the integral from 1 to infinity of 2 over x times x plus 1 dx, which is the same thing as the integral from 1 to infinity of 2 over x minus 2 over x plus 1. And if we can show that that integral converges, then we know that the series converges as well. Well, now that we've already done the partial fractions, the integral is not so bad. The first term is going to have an antiderivative 2 log absolute value of x. And the next term is going to have antiderivative 2 times the log of the absolute value of x plus 1. And we could even simplify that just a little bit further using our log properties. We could write that as 2 times the log of x over absolute value of x plus 1 from 1 to infinity. And if we plug in our limits, we'll have the log of log of infinity over infinity plus 1. Again, that really should be a limit, but I'm using the shorthand of just plugging in infinity to represent the limit, minus the log of 1 over 2. And so it's that first term that's ultimately going to matter. We need to look at the limit as x goes to infinity of log of x over x plus 1. And in fact, you can show that that thing inside of the log is going to approach 1. And we can do that by just pulling the log part, which doesn't depend on x, out of our limit. And if x is going to infinity, the absolute values really aren't necessary there. And that's an infinity over infinity. You could use L'Hopital's rule. You could divide by x on top and bottom. In either case, you're going to see that that's equal to 1 inside the log. And what's the log of 1? It is 0. And so this must, the integral must be some finite number. And if that is the case, well, what does that tell us? Well, if the integral is finite, then the sum must be finite as well. So this one converges by the integral test. Okay, so now we've solved that same problem two ways. We showed that it converged by recognizing that it was telescoping, and we showed that it converged by using the integral test and comparing to a convergent improper integral. We don't even have to stop there. We could also use comparison tests, direct comparison test here. We had 2 over n times n plus 1, which is the same thing as 2 over n squared plus n. Well, notice that is less than 2 over n squared, since the denominator is larger on the left. Well, we know that the sum of 2 over n squared is, well, that's just a p series with n equals 2 with an extra constant of 2 outside. So that's convergent. And so again, we are smaller than small. We must be convergent. And you could use the limit comparison as well. So I show you this example to demonstrate that there's often more than one way that you can solve these sorts of problems. Often there are multiple tests that can be applied. And your approach should be to use the most informative and or easiest test available. In this case, recognizing that it's a telescoping series is probably the best option because we can determine that it converges and that it converges to 2. But if that fails, if you don't see how you can use that, there are some fallback techniques. All right, we'll do some more examples in the next video.